So you can warm up the engines for this wonderful lecture, and we have about 2 minutes, but I think I can. There's not a need for such a presentation for Professor Valerii Vinokur, who will speak about topological nature of high temperature superconductivity, and I think maybe we can start anything you think is appropriate for the people online.
Thank you. Ladies and gentlemen, good morning. And first of all, I would like to express my gratitude to Professor Ali Genscher for inviting and having me here. This is one of the major events, if not the major event of the year, and it's the many-year tradition, so it's a real pleasure to be here again and meet all the friends. Old friends, that's really remarkable. So thanks again, and let's get started. Yesterday, in his beautiful talk, Professor Ivan Božović gave pretty good account of what was happening in high temperature superconductivity. He gave a beautiful list of the unresolved problems, which pose the major puzzle for the modern condensed matter physics and go even beyond condensed matter physics. Then he gave a beautiful list of theories put forth by best minds working in the field, and demonstrated that none of them is actually working to resolve all these puzzles. And what we're going to do today is to, so you think this will be better? Is it? Does it work? Okay. And so what we're going to do today is to resolve all the puzzles which Professor Božović outlined yesterday within the unified and simple approach. So let's get started. Okay, can we make it moving? Oops. Okay, so sometimes it works. Okay, so those are my collaborators with whom we completed this work. Cristina Diamantini and Karl Truppenberger. And those are people who I obliged a lot for their beautiful discussions. Duncan Haldane, and then my good friends Michael Kosterlitz and Tony Leggett. And just like a small words before we start, the real voyage of discovery consists not in seeking new landscape, but in having new eyes. And let's try to look at all what we had with new eyes. Well, my French is rusty, so I wouldn't reproduce this in pure French. Maybe Catherine can do it for me, but not I myself. Okay, let's see. Okay, here we go. So let's take like new eyes and look at something which seems not to be connected at all with superconductivity. This is the old notion of the electric magnetic duality. So those are Maxwell equations. And if you look at them, you immediately see then that in a vacuum, there is a complete, and where there are no charges at all, there's a complete electric magnetic duality, which becomes a little bit, less pronounced if we go to the matter. Then what we need for this duality to be continued is to introduce the magnetic charges, but then, well, it's not quite consistent with the quantum theory. And, well, because quantization exploits the canonical Hamiltonian formalism, well, this problem was resolved by Paul Dirac, who introduced what we now call magnetic monopoles, so I won't stay long on it. It's a beautiful concept of magnetic charges. Everything is extremely beautiful. Only one thing is missing. Those are monopoles themselves. Somehow nobody could see them. Okay, So this is our like strange look from the outside, having nothing to do with the superconductivity. And this, okay, since we entertained ourselves with this like, look already, let's continue a little bit more. And okay, let's see how we can okay compose okay gauge quantum theory recovering electromagnetic duality using okay using Dirac monopoles. We can do it right away and introduce Dirac quantization conditions. So again, monopoles could exist. Monopoles could be incorporated into the standard quantum theory. And again, the only thing, nobody saw them ever. Now let's start with the superconductivity. So, okay, it was a beautiful review written in 2015, okay, sort of overviewing what is going on in superconductivity. It was absolutely beautiful review written by the leaders of the field. So on one hand, okay, this review gave strong impression that the grants which were used to resolve this problem were not like spent for nothing. And okay, and there is some progress. On the other hand, this review didn't close the way for obtaining new grants and actually admitted that, well, the understanding of high TC superconductivity is still absent. Then, okay, to confirm this, the state of the art didn't change by now. So this is like another recent review. And this is what was, okay, the very beginning of the abstract that despite of the efforts, of almost 3 decades, the problem of high temperature superconductivity is still not resolved, and the phase diagram is still not understood. Okay. So one of the things which is like not explained enough is the nature of a pseudogap state, which is viewed to key to understand the nature of high temperature superconductivity. And there are several puzzles. I'm not okay going to list all of them. This was done by Ivan Božović yesterday. So one of them is this Fermi liquid-like behavior, which appears in this region when the pseudogap state is fully established. Then its nematicity and magnetoelectric effects, which don't find the explanation. Then another thing, which Ivan mentioned yesterday, that actually charge carriers, even in the pseudogap state, are probably Cooper pairs because they carry the charge to E as he established by beautiful noise measurements, and it's still not quite clear why it should be so. And so we start with this, and then we will try to resolve all the other problems. So what is well established is that we have antiferromagnetic mode insulator at low doping, and then somewhere we have this quantum phase transition probably from the mode insulator to superconductivity, and then everybody agreed to that it is this quantum phase transition which dominates the physics of high temperature superconductors. And therefore, in order to try to resolve all the problems of high temperature superconductivity and explain what its mechanism, we will apply all the machinery for the description of superconductor to insulator transition and started with a brief overview. So this is just the codic data where this superconductor insulator transition was observed by Haviland Yu and Alan Goldman. This is indeed the iconic picture. There is data from other different materials. And now it's a little bit forgotten because this discovery was a little bit in the shadow of developing high temperature superconductivity, but basically the existence of this transition, superconductor insulator transition in two-dimensional systems, so sort of contradicted to what was believed to be the true from our usual textbooks. Nevertheless, a remarkable understanding was achieved thanks to Matthew Fisher. Oops, sorry. Now, let's try to stay here. So basically, Matthew Fisher gave a very beautiful qualitative picture of superconductor insulator transition. So he said, well, there is a transition between the state where we have condensate, Bose-condensate of Cooper pairs, to the state where we have vortex condensate and localized Cooper pairs, which is opposite to pinned vortices in superconductors. Well, it's a beautiful concept, and our belief in Matthew genius was so high that nobody actually thought how this could come, that vortices which are classical formations and have normal core can get condensed. Everybody believed in it, myself included, and in some sense it's still correct. And then he noticed that there should be a critical point at which the resistance per sheet resistance per square is just quantum resistance, and that this critical point actually can sometimes spread into an intermediate metallic phase. Okay, let's move further on. And then it was absolutely fantastic paper and pioneering paper written by my collaborators who investigated the superconductor insulator transition in the very well established experimental system array of Josephson junction array. And what they beautifully found was that actually the electric magnetic symmetry recovers completely, at least at zero temperature, and that a new phase, which they called super insulator, appears on the insulating side of this transition. And this super insulating phase is an absolutely opposite or mirror twin of superconductivity, meaning that if in superconductor we have infinite conductance, then in a super insulator, by the same token and with the same accuracy, we have an infinite resistance. And they looked at that as indeed the duality between vortex and Cooper pair behavior. Well, to go a little bit further and to construct the full theory of superconductor insulator transition at finite temperature, actually, well, one can just, go along the route outlined by Emmy Noether, another greatest mind of 20th century. Just using symmetry consideration, we can immediately write down the action, just exactly the same way it's done in all the textbooks, and immediately see that we can indeed recover all the magnetic electric duality. So this action actually doesn't contain anything miraculous or unusual. Okay, we have the usual kinetic terms as in any textbook. Then we have, well, people working, for example, in charge density waves know, very well that, we can, together with the term describing, let's say, elastic properties of charge density wave and the potential energy of the related to the phase of the charge density wave, we have to have crossing term responsible for the mass, for the topological mass. And we exactly have this Chern-Simons term here, just quantifying the Aronoff-Bohm interaction, which was its importance for the superconductor insulator transition was overlooked. And we have it there. So this is completely dual action. And basically it encodes all the physics of the superconductor insulator transition and goes and describes all the phases which appear near the point of superconductor insulator transition. And this is the summary. So we have, come back. Yeah. So basically we have at zero temperature, 3 phases. We have superconductor, we have super insulator, and we can have topological insulator which is actually, okay, at the same time was a metal phase. And this topological insulator appears only at high values of some parameter eta. And it's a beautiful parameter because it combines the strength of the quantum fluctuations and just the geometric characteristics of the system, which encodes the material properties. So there are three phases next to this transition: superconductor insulator transition, and what we can say, now we can turn to superconductivity. And we can ask the question, how do monopoles? One thing more, sorry, which I forgot to mention. If we do now the exact theory of the superconductor insulator transition, then we can immediately see that instead of duality Cooper pairs vortices, the true duality is Cooper pairs magnetic monopoles duality. So in a superconductors, we have Bose-condensate of Cooper pairs, but in a superinsulator, we have a Bose-condensate of magnetic monopoles. Then our electromagnetic symmetry is full, and this is the full description of superconductor insulator transition. And of course, the only question is, how do monopoles, which nobody saw ever, appear in condensed matter physics? Well, just to give an illustration to that, we can consider a simple picture, what is going on when we apply magnetic field to type 2 superconductor. Well, we know that vortices form there, but the way we can look at the vortex is that the vortex is made by two monopoles from the two sides of the same and then Cooper pair condensate just like squeezes magnetic lines into this filament, which we call vortex. And exactly the same happens in a superinsulator, but just the opposite. If we have two charges, then the current of monopole condensate squeezes electric lines into the electric strings. And actually the strings are very well known, people doing field theory, those are Polyakov string. And those are exactly Polyakov string, which prevent charges from moving, because if you try to take them apart, this string tension, it doesn't allow them to move. That's why we have infinite resistance. Okay. And how do monopoles form inside the materials? Well, the similar way, if we have a usual vortex, it can turn if we have a layered structure, and then the ends of this vortex can be viewed as a monopole, and vortex itself can be considered as a Dirac string. And well, and then we can say that this topological superconductor superinsulator transition is nothing but inherently quantum phenomenon reflecting full magnetic electric duality. And just, for example, just analyzing the behavior of the Josephson junction array, one can immediately see that the Josephson junction array being held near the superconductor insulator transition is a medium which generates a lot of these magnetic monopoles. Now let's turn to pseudo-gap state. So let's start with this T-squared behavior. This is exactly Fermi liquid-like behavior. And what we know about the Fermi liquid-like behavior is that we should have no other scatterers for these fermions, but fermions themselves. Then we have this usual T-squared. It sounds a little bit strange that we can have such a phenomenon at elevated temperature. And then the only way to explain it is to say that our fermion states are topologically protected. State means that there are some surface or boundary states. Now, the possible states we know that can appear near the superconductor insulator transition, and remember we decided that it is the superconductor to insulator transition which dominates the behavior of the high TC behavior. The first phase which appears there are superconductors. They don't carry any surface states, so it doesn't work. Then there is this topological insulator. It also doesn't have any topological bound or surface states. So this phase also doesn't work as a candidate which can describe pseudogap state. Then the only state which remains is this superinsulating state, which looks absolutely counterintuitive, because what the superinsulating state can do at this elevated temperature, well, looks like that. But this is a superinsulating state with one small subtlety. It's not the usual superinsulator. This is superinsulator which demonstrates magnetoelectric effect, which is not explained, I remind you. How we can describe magnetoelectric effect? Well, again, we will make textbook move, and we add what is the term which is called theta theorem, which looks like that. Really, sometimes goes really fast. Okay. So this is well-known magnetoelectric theta term, and the resulting state we can call oblique superinsulator. And you can see, that this occurs from this polarization term. And this indeed describes magnetoelectric effect. And then if we just integrate out our all the gauge fields and find out what is the free energy or first action and then free energy of our oblique superinsulator state, we find out that within this state, there are two kinds of carriers. One of them are diams, the particles which carry both magnetic and electric charges. Another term which presents like in this action and then in this free energy is monopole current. And then we have this free energy where we have the term of diams and terms thanks to monopoles. And looking at this energy, we can immediately find the condensation condition. So it means that these two terms should fall within this ellipse. You understand? It means that either this term or that term make the full free energy negative, and then the kind of carriers which makes the free energy negative cause boson condensation. So this is the condensation conditions. So what we can have either diams condensate or monopole condensate, and depending on what happens there, we will have like one or another state. And this is once again to remind you where monopoles are coming from. And this is the form which the current assumes due to this theta term. And then again, I remind you that means in the presence of this topological theta term responsible for the magnetoelectric effect observed in the experiment, we have diams which acquire both electric charge and magnetic charge. And this is very well-known effect. It's called Witten effect. And then we immediately understand where this our T-square behavior appears from. Because this phase near the superconductor insulator transition should have granular structure, then we should have surface or bound state topologically protected. Diams at the boundaries of these bubbles acquire fermionic statistics, so they form Fermi liquid. And since they're topologically protected, they behave exactly like a Fermi liquid. And this is exactly where this T-squared term appears from. So one of the problems is immediately resolved. The problem about the nematicity and magnetoelectric effect is resolved as well. This is exactly due to this term. And we can move further on. So this is where we have the full description of phase transitions which occur in this high temperature superconducting state. So depending on the strength of our Coulomb interaction, which we can vary, for example, changing either the temperature or the doping, we can have either superconducting state where these Cooper pairs make a condensate, then we can have transition between the states, and we can notice that when we have this transition, which includes coexistence of dion condensate and Cooper pair condensate, our parameter eta is less than 1, and it means that this is a direct transition not involving any intermediate phase, exactly as we see in the experiment, or we can have oblique confinement, and this means that we have this oblique superinsulator, which is a pseudo state. If we have finite temperature, then the ellipse size shrinks together with temperature, and then we immediately obtain all the transition from the pseudo state to a normal metal, or transition from a superconductor if we are in an overdoped region again into the metallic state. Now, one detail. Okay, how I'm doing with the time? How much time do I have? 15 minutes? Good. Okay, now, one small detail. We know pretty well that all these layered materials, if we study some microscopic effect, some like Hall effect in the usual high TC superconductors, which is like measured by usual means, or like if we study quantum fluctuations near the superconductor metal transition or something like that, we see absolutely like two-dimensional behavior. This is now probably a subject of textbooks. But at the same time, this monopole-related behavior we were talking about, this is essentially three-dimensional feature. Without mentioning monopoles, actually, Ivan Borovich was mentioning this himself. And this is exactly what we have in our description. And you can immediately remember, for example, that the elementary cell of like any high temperature cuprate actually has two cuprum oxide planes. And this is exactly what we need for this our three-dimensional behavior, which is described by the monopole action. So in terms of the microscopic physics, we do have three-dimensional behavior, all right. Now we can immediately say why we now understand, this is the first stage understanding, why our superconductors are high temperature superconductors. Because these dions, or monopoles if you wish, play the role of the glue who makes Cooper pairs stronger. It's just like some additional thing which like prevents the splitting into the single carriers. And then, of course, we immediately understand why in the underdoped region, sorry, we have these Cooper pairs which go well above superconducting transition temperature because they go there as dions. And then this model or this description describes another remarkable thing. We know pretty well that if we take a single layer, for example, of biscuit containing one unit cell, then it's going to show the exact, well, not exactly, but practically the same superconducting transition temperature as the bulk sample. If we take the ordinary superconductor, you will never see that. If you make a thin film, of an ordinary superconductor, its transition temperature is going to be much less. And the explanation, I repeat, it's just because this monopole gluing, it's enough to have just two cuprum oxide planes. We don't need any more. Okay, let's move on. So this is just to repeat once again that even a monolayer high TC material shows exactly the same transition temperature. Well, there are some wise words which I don't want even to read because I'm not sure that this early morning I remember what does it mean non-abelian nature. Well, complicated words, but okay, those who like it may read it. I'll give you a minute and then we move on. Read it. That's good. Now, a little bit more. Ivan mentioned a couple of more puzzles over there. One of the puzzles, okay, I'm not going to describe all the puzzles which he mentioned. For that, probably we will need a course of lectures, not just one short talk. But one of them was the following. Suppose we are in a overdoped region. Suppose we applied magnetic field and destroyed superconductivity. And then we measure the resistance and it's linear. And then it was, okay, this kind of resistance shows both magnetic field and temperature dependence. Then this was this universal behavior of this linear resistance and, okay, going to really low temperature. And this was sort of like, okay, unknowingly ununderstandable where it comes from. If now we remember the nature of the high temperature superconductivity, which we now know, it becomes immediately understandable. Okay, first of all, we have to remember that in the presence of magnetic monopoles, the Cooper pairs, so you remember we destroyed Cooper pair condensate, so the Cooper pairs which survived and now exist outside the condensate. In the presence of monopoles, they become fermions. Now, when we applied high magnetic field in this overdoped region, we did destroy Cooper pair condensate, but we still have Bose-condensate of dions. They are stronger and they're not destroyed by this magnetic field. They survive. And how do they behave? Well, like the usual bosons. So if we have fermions and bosons, what do we have? We have fermions, like our Cooper pairs, which are scattered by bosons. This is, again, textbook knowledge. This is exactly like the usual electron-phonon interaction. And if we are at high temperature, which exceeds this Grunizen or block Grunizen temperature, then we should see the usual standard textbook linear behavior with the scattering, universal scattering time like that. Like, okay, the only thing is just the coefficient may be different. And if we just estimate what is this block Grunizen temperature for these fermions, which are now Cooper pairs, we'll find out that this temperature is actually quite low. And that's why we can see this linear behavior going down to really low temperatures. Now, okay, this residual of this dion condensate Bose particles which work like phonons, they called bogolons. This is also a well-known name. And this is where we exactly have this universal scattering time and this linear behavior. So this puzzle is also resolved. Now, the behavior of the magnetic field, well, this is, sorry to say again, is nearly trivial because everybody who was studying, for example, let's say, fluctuation behavior near the superconductor insulator transition knows pretty well that if we go to low magnetic field and where only temperature effects are important, we can immediately find out all this, like, what is called quantum correction. And if we go then to very low temperature, but high magnetic field, but also near this, line of Hc2, we immediately reproduce exactly the same formulas, but with one replacement. Instead of temperature, we have to substitute like this magnetic term, because it's just like the switch between the generation of the states due to temperature to the generation due to magnetic field. And it immediately means that we have this, two terms, one linear in the resistance and another one is linear in magnetic field, which has sort of like this, Bogolon-like origin. And that's why we do have this resistance, which is the sum of the linear in magnetic field and linear in temperature. And probably this is almost all. The only thing which is missing is, how's about the pairing mechanism? Everything looks like great. We explained, well, and those things which I didn't mention today can be explained just applying the same technique and the same kind of reasoning. The only question which we didn't answer yet is where this pairing itself is coming from. Well, remember that we should have this three-dimensional picture. We should have like these two conducting planes, which are close to superconductor insulator transition. And this means that these planes should generate monopoles. And then we can immediately assume and try to see what will be the result, that the same monopoles which offer an explanation of all these possible properties of high temperature superconductors play actually the role of the source of pairing. And then, there is a, let me see if I mention it in my previous slide. Yeah, well, yeah, let me say it here. On one hand, if we have a three-dimensional material, like layered material, layered superconductor, and which is close to high temperature, close to superconductor insulator transition, then we have monopoles which appear in the system in a natural way. But then there is another source of monopoles, which probably discussed in the literature, 5 minutes, related mostly to graphene, which can be viewed as a source of what is now called pseudomonopoles. And the source is the following. Suppose, that we have, for example, it's usually considered within the framework of this like graphene sheet. So suppose we have some material. Suppose we have some defects in this material, like dislocation. What is, the beautiful description of the effects related to topological defect is material is actually was suggested by probably general relativity theory. You can describe the distortions introduced by the topological defects in the lattice as a curvature. And this curvature, and it was shown like 100 papers dedicated to graphene. And this curvature is equivalent to pseudomagnetic field. And if you attentively look what kind of this pseudomagnetic field is produced by these topological defects due to this curvature, this is exactly the monopole-like magnetic field. So we can say that if we do have these defects, topological defects, for example, in the cuprum oxide plane, then we immediately have local pseudomagnetic field, and it means that we do have these pseudomonopoles there. And then we can consider a very simple model. Actually, it's again for the standard quantum mechanical course, a simple quantum mechanical problem. So consider two conducting planes which has this pseudomagnetic field, and then it means that in between this plane we have this pseudomonopole, which exactly produces this pseudomagnetic field, which describes this curvature caused by the topological defects there. This is a simple quantum mechanical problem because this monopole, pseudomonopole, and its magnetic field, pseudomagnetic field, is going to bind to electrons located in this opposite field, planes, and we can estimate the binding energy is this one, and this is the distance between these planes, which is of the order of the electron wavelengths, and then we immediately see, that this energy is actually up to the numerical coefficient. This binding energy is sort of like of the order, or maybe 10 times less than the Fermi energy of the electrons, meaning huge. And if we make, solve this problem a little bit more precisely, I didn't want to bother your attention with this sophomore quantum mechanics, but if you find, the solution and give an estimate, then you'll find for transition temperature that it should be at least 100 Kelvin. This is basically exactly what we see in this high TCs. Oh, by the way, this resolves one more puzzle of high temperature superconductors. We know that unlike in the usual superconductors, where the psi coherence length is much larger than the distance between the Cooper pairs, in high temperature superconductors, this is absolutely the opposite. The psi, the size of the Cooper pair, is less normally than the distance between these Cooper pairs. There was no explanation why in high temperature superconductors it should be like that. So, this is the explanation. So one more result is just solved. One more puzzle is solved just by passing. See, do we have something else, which is the rest? No. So basically we can stop here. And since there are still a lot of things to do, for example, experimentally, because we can check whether these monopoles or pseudo-monopoles are indeed there, and we design different kind of experiments, but it will be a little bit too premature to discuss this in detail. So I leave it without the conclusion, because let's work together further on. And stop. Thank you for your attention.
Thank you for such a wonderful lecture. I think we are ready for some questions. One, two, one, please.
What is the interaction of this general picture with well-known properties of electronic structure of cuprate superconductors? I mean, in first time, this is Pavarini-Andersen correlations between the cuprum 4s level and the critical temperature. Another problem which has to be explained in a general picture is the anisotropy of ARPES with the spectral lines along the Fermi contour. And also, if it's possible to explain this anisotropy of scattering rate, it's possible to calculate from this general picture the Hlubina rise and Ioffe-Millis phenomenology of cold spots or hot spots. So a lot of things has to be do. And what is the perspective? This general picture to explain already well-established properties of electronic structure.
Thank you. An excellent question. Okay. Okay. First of all, as I said, I didn't want to bother you with this, like, okay, sophomore quantum mechanical problem. But if you write down what is called like Pauli equation, well, just the generalization of this like Schrödinger equation for the electron which is caught by the monopole, you will immediately see that the electrons which are paired or bound in the potential well make like d-wave. They have this angular momentum which makes them d-wave. And therefore, that explains why these our cuprates are indeed d-waves. Now, at this point, since, okay, one thing, okay, there are many well-established facts which they don't contradict, but we didn't have enough time, having only 6 hands, to like, okay, our theory is like quite simple. It's just like, can be formulated in 3 lines. However, the explanation of like all the properties and all the calculations, it's like exactly, I think it's some good 5 volumes or that thick where some calculations should be done. And you're absolutely right. We have to, there are no like contradictions between all the properties which you mentioned. They were not just calculated, but since even D-wave superconductivity is obtained in one line from the simple equation, then we have just, okay, to sit down and to calculate all the rest. This is the answer to your question, and I hope that this will be done like by enthusiastic students.
Thanks, Vitaly. Just a simpler question. Basically, what you are saying that we should concentrate on two-dimensional materials mainly, because when we have 2 dimensions under control, and according to your theory, everything, then we can just basically play the Lego. But 2 dimensions is the key if we really dominate it experimentally.
Thanks. Another good question. Well, not quite, because exactly the same picture applies to pnictides. Basically, what we have to say is just the conducting planes, but the material, but by its properties, can be completely like isotropic, so to say. This, okay, applies very well to pnictides, exactly the same. What I was saying, that the minimal model to explain all this is just to say 2 conducting planes, which is actually 3D. Quantum mechanically, this is 3D. And this is the minimal model to obtain all the properties. If we add the stack of these planes, nothing's going to change.
Thank you. We have some questions online. Let me read the first one. It's from Roland Wiesendanger. And it says, does this theory have predictive power besides being descriptive? I.e., can a strategy be derived for the search for novel classes of superconducting materials with Tc above room temperature?
Oh, sorry.
That's,
I see. Yes. It does have a predictive power, I believe so, because we can, for example, outline the ways of going even higher transition temperatures than what like these cuprates show us. But this probably, well, will be a little bit premature to like to tell about detail, but the answer is strong and positive yes, because we know how to increase this estimate. I mean, this is the simplest thing.
There's another question below,
Question to speaker.
which is quite long.
Road using custom. Wow. Well, sounds quite interesting. I'm not so like, okay, self-confident as to try to immediately resolve it right away. But seems, yeah, okay, this explanation may be, okay, quite plausible, what the author of the question proposed. But well, indeed, I'm not like, okay, self-confident enough to give strong yes or no. Well, and if we can use this effect to make a battery, wow, this should be a content of strong patent. And then again, I leave it to the author of the question. I don't want to interfere.
Thank you. We have another question now in the audience. Yeah.
Yes. I answered. Okay, good. Sorry.
Okay. Thank you very much. Oh, there's another question. Sorry.
Oh.
Sorry. Please.
Well,
Such an interesting topic. Deserves many questions.
Do dyons exist at heavy overdoped regime and play the same role?
once again, please.
Do dyons, your quasi-particles with monopoles, exist and play the same role at heavy overdoped regime when the material is like fermi-liquid?
Yeah, they do exist. Okay, it's remains of this, okay, dion condensate, yes.
But the temperature of superconductivity is quite high.
Yes.
Even their role is almost negligible.
Why?
Because the quantity is too small. No?
No. Okay, they still play a role because, yeah, because they play the role of phonons there, as we saw from this linear dependence of the resistance.
Okay, and you say that two copper oxygen 2 superconducting planes are necessary, but in yesterday lecture, they say, Professor Bazubazovich said that only one plane is already superconducting. What is his explanation? Could you explain?
I think that, well, okay, unfortunately, he is not here with us, but we were discussing this like a lot. And I think that basically what he had in mind was that the layer with a, okay, let's put it that way. I don't have, okay, I think that what he had in mind was a single, okay, elementary cell of cuprate is enough to have, okay, superconductivity. Because I don't have, maybe I'm missing something, but I'm not aware of any experiment where people were capable to cleave one cuprum oxide plane and do experiments. I was a part of all these experiments. For example, they were done by the group of Philip Kim at Harvard. And one of them, we were measuring Hall effect on these like layers. Okay, so the best system at the time when we published our work was the system where we have 2 unit cells there. So meaning 4 cuprum oxide planes. After that, now I know that there are some experiments which he had done on the single layer, but this single layer is a single unit cell, which like, okay, which include 2 cuprum oxide planes. And I'm not aware of anybody else who can do experiments better than this group. So I believe that what Ivan had in mind was just like a single unit cell.
Thank you very much. It's great to have your presence here with such a provoking and wonderful lecture. And we have a diploma that is given
Thank you very much
to everyone.
Thank you.
Thank you very much. And thank you all.